Hello guys, how are you today? So today I'll be explaining chapter 9 summary. So the title of this video is gonna be chapter 9 summary for chemistry. Okay? And I just want to say in advance, I apologize for not posting the past few days because I've had a competition. And anyways, let me just start explaining chapter 9 summary. So in chapter 9, we learn about bonds, okay? So we have two types of bonding or two types of bonds, okay? One here, one here. The first one, we call it intermolecular bonds. So intermolecular bonds. Now what about intermolecular bonds? They occur between, so this is a key word, they occur between molecules. So I apologize, I don't know what is happening. So, intermolecular bonding occurs between the molecules, okay? So there is a difference between within and between the molecules. Now, the intermolecular is represented as this. So you're gonna open your brackets and you're gonna represent the bond as dot, space, dot, like not dot, a line, space, and a line, space, and another line, space, and etc. And usually the forces between intermolecular or the forces between the molecules, they are van der Waals forces. So we call these van der Waals forces, or in another term, a shorter term, it is VDW. So for now, we discussed intermolecular bonding. It occurs between the molecules. It's represented as dot, 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 or like line, space, line, space, line. And the forces is usually van der Waals forces, which is a very weak force, okay? For now, we don't need to understand what are van der Waals forces. We just know that this is a scientist. He discovered these forces and it's named after him. And we know that they are very, very weak forces applied between the molecules. Okay, now on the other side, we are going to discuss intramolecular. So we have intermolecular and intramolecular. Now, the difference between intermolecular and intramolecular. Intermolecular means between the molecules, whereas intramolecular occurs within. So occurs within, this is our new keyword, the molecules. Okay? So intermolecular means between the molecules, intramolecular means within the molecules. Now, it is represented as a straight line. So if we want to represent the intramolecular bonding, it is represented as a straight line like this. And the forces that usually occur in intramolecular bonding, they are called covalent bonds or covalent forces. So just write covalent bonds. Okay, and usually covalent bonds occur between two non-metals. Now, this is the first page done. We move on to the next one where we discuss the types of intermolecular bondings. So the title of this page is gonna be Types of Intermolecular Bonding. So the types of intermolecular bonding. First thing, we start with metals. Okay, metals have a metallic bond. So this is very simple, very easy. We know that metals have a metallic bonds. Next one, we move on to our ionic compounds. Okay, so what about ionic compounds? They have ionic bonds. So far, it's really easy. So metals have metallic bond, ionic compounds have ionic bonds. Okay, now here we move on to something different. Non-metal compounds. Okay? Or atoms even. It doesn't have to be necessarily a compound. So non-metal compounds or atoms. For example, we have monoatomic, which is what? Which is the noble gases, for example. The noble gases, which like helium, neon, argon, krypton, whatever, you know. Or the polyatomic. Okay, so any example of polyatomic will be, for example, H2, S8, etc. All these types of polyatomic, they share one type of force, which is van der Waals force, which we said are very, very weak forces, okay? Now we move on to something different, which is carbon, for example, diamond, graphite. So I'm just gonna write diamond. So carbon, an example is diamond, or SiO2. They share what? They share covalent bonds, or they have covalent forces, or the forces of covalent bonds in between them. And now, last but not least, we have molecular compounds, okay? They have a force which is the van der Waals force. So this is pretty much it for the types of intermolecular bonding. So we move on to the types of crystalline solids. So this is very important. Types of crystalline solids. Okay? So the first type of crystalline solid that I believe everyone knows about is ionic solids. Now, what about these ionic solids? We know that ionic solids occupy lattice-forming giant structures. So all you need to know about ionic solids and the crystalline solids is that they occupy lattice-forming giant structures. Okay? Now, what does it mean that they occupy a lattice-forming giant structures? Very simply, it means that the ionic solids take the shape of a lattice. What is a lattice? A lattice is a giant structure where it repeats itself in all directions, okay? And they all have like the same forces in all of it, so they form a normal, or not a normal, what was the word? A constant or uniform, that was the word. A uniform structure. So for example, a cube, a hexagon, anything like this, you know? This is what it means they occupy lattice-forming giant structures. But the difference between the ionic solids is that the lattice is made out of two charges, which is the cation and the anion. So they have the force of attraction between them, okay? And as we said, these are the ionic bonds forces, okay? They have these forces of attraction in between them that will like cause this lattice to form a giant structure. So this is ionic solids. Moving on to the next one, we are discussing molecular solids. Okay, so what about molecular solids? Now, a molecular solid, okay, has discrete covalent molecules that occupy lattice points. Now, what does this mean? This very simply means that molecular solids do not have a network. They are not a network solid, very simply, because a network solid is where all the atoms are like bonded to 4 other atoms or 3 other atoms, or like, and it's this constant repetition to form a lattice. Whereas molecular solids, they are molecules, okay, that they form together. So let's take an example. H2O, when you freeze it, it becomes ice. So H2O is liquid water, but when you freeze it, it becomes ice. And ice, you know, you can shape it and whatever. But if you look into the molecules and whatever of H2O, liquid, gas, or ice, it will form a lattice. Or another example is sugar. Sugar is C6H12O6, okay? So like sugar in its regular form, it forms a crystal, but actually it's not a network solid, first of all. It's a molecular solid that is like a bunch of molecules of sugar just like filling in the lattice points. This is what it means very simply. Now, of course, if it's not necessary for you to explain, you just need to know that discrete, which means individual, discrete means individual covalent molecules. For example, C6H12O6, here, but they are individual, okay? So discrete covalent molecules occupy lattice points. I think lattice is double T, I don't know. Okay, so the thing you should know most is that molecular solids are very simply not network solids. Now we move on to the rest. The rest are just gonna be simple definitions, so I'm gonna write them quickly. An atomic solid is a pure element. So pure elements, for example, They are atomic solids, for example. I cannot think of one, let me think. Pure phosphorus, pure sulfur, pure carbon. But carbon is a special case. We're not gonna go into it. You cannot say that carbon is an atomic solid. Later we will discuss why. Okay. Pure, I don't know, just anything that's pure. For example, like pure sulfur, phosphorus, pure elements in general. Now, metallic solids, as you can guess, they are just like metals. Okay, so they are metals having metallic bonds that form giant structures. So, metals forming giant structures. Okay, and then now we move on to the network solids. What about the network solids? Network solids, they form uniform lattices, okay? But these lattices, they are like special types of lattices. Or, excuse me, or in another sense, network solids, they are like, as I said, lattices, but they are covalently bonded in continuous extended 3D networks, okay? And they are like one giant molecule, unlike the molecular solids where we said it's molecule here, molecule here, like a bunch of molecules all together, and they will form the molecular solids. A network solid is just like one giant molecule. It's a bunch of atoms just bonded all together. It's not like a molecule bonded to another molecule and etc. No, it's a bunch of atoms bonded all together to form one giant molecule, which we call a network solid. Now, I'm not gonna write the full definition of network solids. I'm just gonna write a giant structure. And one last thing I'm just gonna add over here is group 8A solids. So group 8A meaning, now we do not have to learn or understand what are group 8A solids. We are not required. We just need to know that group 8A solids, okay, they are like noble gases that form solids. Okay, so now we move on to the definition of a lattice. I've discussed the definition of a lattice before, so I'm just gonna write it quickly. A lattice is what? Okay, I will tell you a long version and then I will try to simplify it. So a lattice is a giant structure where it repeats itself in all directions and all forces are the same in all directions, holding the structure together. So very simply, we can say a lattice. It is a giant structure. Okay? Where its composition, I'm gonna say composition in this sense, and forces are repeated exactly the same, or just are repeated the same in all directions. So a lattice is a giant structure where its composition, meaning the molecules or like the atoms or whatever, are repeated, and the forces that are between these atoms, molecules, etc., are repeated the same in all directions, okay? And they form, or sorry, these forces form what? They form a strong, one big strong force that holds the whole structure together. So holding the structure together. Okay, so now, sorry. So now we will move on to discussing each one by itself. So very quickly, I'm just gonna say again, what is an ionic bond? An ionic bond is an electrostatic force. So what you just need to know is that it's an electro. So again, ionic bonds are electrostatic. I don't know what I wrote. Oh my goodness, wait. How do I erase? So again, ionic bonds are electrostatic forces, okay? And usually it occurs between the cation plus the anion. Okay, so again, ionic bond is an electrostatic force that occurs between the two opposing charges, which is cation and anion. So now we are gonna go on to the properties, okay, of ionic crystals. ionic crystals. Now, what about the ionic crystals? What you need to know that the ionic crystals in general, they are hard crystalline or crystalline. Sorry, I don't know, I cannot write today or spell. Crystalline solids. So, properties of ionic crystals. First is that they are hard crystalline solids. If they ask why, it is because ions of opposite charge, okay, are next to each other. So there is a strong ionic bond. So hard crystalline solids because of a strong ionic bond. Why do we have a strong ionic bond? Because the ions of opposite charge are sitting next to each other. Okay? So this is a D, by the way. Alright? Then we have the ionic crystals have high melting or boiling points. Okay? If they ask you why do they have high melting and boiling points, again, due to the strong ionic bonds or the strong forces of attraction. Why? Because the ions of opposite charge are sitting next to each other. So they will have a strong ionic bonding, and due to the strong ionic bonding, they have strong electrostatic force. And the stronger the force, the higher the melting point, because when you are melting or boiling, you are basically breaking the bond, and you need a higher amount of energy to break the bonds. Now, they are also usually soluble in water. Okay? Now, why are they soluble in water? Very simply because the water molecules can bind with the cations and anions. So usually you know that H2O, for example, plus NaCl, and then you're gonna switch them up. So it's gonna be 2HCl plus Na or something like this. You know, these equations that we have taken before. I don't believe what I just wrote is correct, but it's just like an example to make you understand what they mean by that it's usually soluble in water. It's that the water molecules can bind with the cations and the anions and form new, most of the time they will separate the ions, okay? Or in other terms, if it's not soluble in water, they will create a new product, which is the precipitate, or we call it precipitate. So usually they are soluble in water because the water molecules can bind okay, with the cations and anions, and if they don't bind, then they will form a precipitate. That's why they said usually, but not all the time. Now we are gonna discuss the electrical conductivity. So we are gonna now have a few sentences about electrical conductivity. What exactly about electrical conductivity? First thing, we know that we are talking about ionic crystals, and ionic crystals, when they are solid, they do not have electrical conductivity. Why is that? It's because there are no free electrons, or the electrons or ions, because we're talking about ionic crystals, the ions are not free to move and carry the electric current. So because they cannot move and carry the electric current, they do not conduct electricity. This is very simple. Then we have when it is molten or aqueous, it does conduct electricity, very simply because when it's molten or aqueous, the ions separate, okay, they are free to move, okay, and they will carry the electric current, so then they conduct electricity. Now, another property of ionic crystals is that they are brittle, okay. Now, why are they brittle, and what does brittle mean? Brittle means they are hard, but they can break. So brittle means they are hard and they can break. Now, why are they brittle? Because the structure of the ionic crystal. Okay, so we know that ionic crystals are how? We have two ions. Let me just make something small. So 1, 2, 3, and 4. Let's say something like this. Then we have something again. 1, 2, 3, and 4. And it will go on like this. So this is what is forming the ionic crystal. Now let's say the red is positive and the black is negative, okay? Now what's gonna happen is we know that positive and negative attract each other. Whereas if you notice here, this is also positive and this is negative. So between the layers, there's gonna be a force of repulsion that causes them to break easily. That means they are brittle because there is a force of repulsion in between the layers. So they are hard, Yeah, like you hold them, they are hard because of the strong attractive forces between the ions sitting next to each other. But the ions that are on top of each other, they are the same charge, so they're gonna repel each other. Okay, and this causes them to be brittle. That means they can break easily. And that is pretty much it for ionic crystals. So now we will move on to covalent crystals. First, let us define covalent bonding. So covalent bonds or covalent bonding, it's very simply the sharing of electrons, okay, between two nonmetals, okay, to achieve noble gas configuration. Okay? So this is the definition of a covalent bond. It's the sharing of electrons between two nonmetals to achieve noble gas configuration. So I think I will open a new page. I'm not wasting paper because this is on my tablet, okay? Don't worry, guys. I might be wasting storage though, but that's okay. Now, the properties of covalent bonds, so I'm just gonna write properties. Sorry guys, I don't know how to spell. I'm not the best at spelling, so I have to keep on checking. Properties of the covalent crystals, okay? First thing, they have low melting points. Now, why do they have low melting points, or like not only low melting points, melting or boiling points? So why do they have low melting or boiling points? It's very simply because the intermolecular forces are very weak. So the energy needed to break the bonds, okay, like is very little. So we don't need a lot of energy to break the bonds. This also means that they are most of the times gases or volatile liquids. All right. However, if they are solids, that means they are insoluble in water, or even the gases and liquids are insoluble in water. However, it is soluble in organic solvents. To be honest, I don't know what an organic solvent is, so just like memorize. It's insoluble in water, but it is soluble in organic solvents. Okay, and also the covalent crystals do not conduct electricity, so do not conduct electricity. And again, I did some spelling mistakes. Electricity. Now, why do they not conduct electricity? It's because they do not have any free electrons that can be delocalized and carry a current. Because pretty much covalent crystals are like sharing the free electrons, okay? So there is no free electrons to be used to make an electric current. Now we will move on to metallic. I don't know how to write it. I'm sorry. Metallic bonds. Okay, so very simply, metallic bonds are what? They are an electrostatic force of attraction between positive ions in a metallic lattice with a delocalized sea of electrons. So I'm just gonna write metallic bonds. It is positive ions. First of all, of course, it's an electrostatic force, so electrostatic force. Okay, so metallic bonds are electrostatic force. They are positive ions, okay, that surround a single delocalized electron. So if I was to draw the shape, okay, let's say this is the electron, then it would be something like this. So positive, 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 and then these are the forces of attraction, and then you have forces of repulsion. Now we are gonna discuss the properties of metallic bonds, okay? So some properties of metallic bonding is that they have high melting points. Now, why exactly do they have high melting? Not only melting, but also boiling. I keep on forgetting boiling. High melting or boiling points. So why do they have high melting and boiling points? It is because very simply of the strong metallic bonding, okay? Now we also know is that they conduct heat and electricity, okay? So they conduct heat and electricity because they have a sea of free electrons. They are also malleable, okay? And ductile. Malleable and ductile means that if you hammer it or like you shape it, you can change its shape without it breaking or cracking. Why is this? It's because if you're dealing with pure metals, okay, pay attention, we're dealing with pure metals, okay, the layers slide over one another. So this causes them to be a bit stretchy, but not stretchy, and like elastic, but not too elastic, because like you can shape it, you can change its shape and everything, and it does not crack. Okay? And then finally, it is shiny and lustrous. What does shiny and lustrous means? It means because, so again, it's shiny and lustrous because free electrons can absorb and re-emit light, which causes the shine. Okay? So now we are not gonna be talking about pure metal, we are gonna be talking about something called alloys. What are alloys? Alloys are metal solution. Examples are steel, brass, and bronze, okay? But because they are impure, they are gonna be harder, stronger, and have a lower conductivity than pure metals. So alloys, we are gonna say they are metal solutions. Examples. Some examples we have are steel, brass, bronze, and etc. All right. And because they are impure, since they are impure, okay, they're gonna be harder. They are harder, stronger, and have lower conductivity than most metals that are pure. Okay? And that is pretty much it for alloys and metals. So now we move on to the network solids. Now, before that, let me just define what are network solids, okay? Network solids, they are giant covalent structures by some elements and compounds, okay? But they form one big molecule. It's not like a bunch of molecules coming together to form a molecular crystal or a molecular solid. No, they are a bunch of elements and compounds coming together, okay, to form one giant molecule. So, to define network solids, it is a giant covalent solid, okay, by some elements or compounds. All right. So now let me just change the color a bit so it's not too boring. We are gonna talk about the two types of network solids. We have atomic, so the basic unit is an atom, and we also have molecular, so the basic molecular. So the basic unit is a molecule. Now, like atomic, for example, we have diamond and graphite because they are both carbon. Molecular, for example, we have sand, SiO2, quartz, and whatever, etc. Quartz, like if some of you guys play Minecraft, okay, it's like especially like when you're building a house. I remember like when I used to play Minecraft, I would build a house with quartz. So quartz is a molecular network solid made out of, now we are gonna see what it's made out of. Okay, now before we get into that definition, we're just gonna know what is allotropy. I don't know if I pronounced it right. Allotropy. Okay, allotropy means when two or more forms of an element exist in the same physical state. So diamond and graphite are allotropes. Why? Because both of them are from carbon. So two or more forms of an element, we are talking about carbon. So if diamond and graphite, two or more forms of element, which is carbon, exist, okay, in the same physical state. So diamond is solid, graphite is solid. In the same physical state, okay? Now, some examples of allotropes, okay? So the form is gonna be allotropes. Oh my goodness, I cannot write it. Okay, allotropes. So some types of allotropes, okay, as we discussed before, from carbon we have diamond, graphite. And now this is a really, really funny name. I don't know how to say it. It's like really funny, but just bear with me. It is called Buckminster fullerene. It's really long and funny for some reason, but just like either say fullerene or Buckminster fullerene. Okay. Okay, now that we were discussing about diamond, graphite, and Buckminster fullerene, we are gonna discuss about actually diamond, graphite, and silica or silicon, okay? And in 3 different slides. So first we are gonna start with diamond. Now, most of you know diamonds, okay? Diamond is used for jewelry, in Minecraft if you find it. By the way, diamond is used when you are cutting glass. So, you know, the glass cutters, they are made out of diamond. All these types of things, you know? Okay, so what about a diamond? What you need to know about the diamond is that it's a tetrahedral structure of linked hexagons. Okay, where every carbon atom is strongly and covalently bonded to 4 other carbon atoms. Thus, there are no free electrons. So let me just write the definition. Diamond, it is a tetrahedral. Tetrahedral means that one is connected to 4, okay? Structure of linked. I'm probably gonna speed this up, so, okay? Okay, so now let us discuss the properties of the diamond, okay? So, diamond has a high melting point. Hold on. High melting point. Now, this is due to what? This is due to the strong covalent bonds, okay? So it has high melting point due to the strong covalent bonds or the strong forces of the directional bonds, okay? It also doesn't conduct electricity as there are no free electrons, so it doesn't conduct electricity. Okay, since there are no free electrons, and it is also hard, like it's really stiff and hard, due to the strong covalent bonds again. So these are the properties of the diamond. Now, some uses, like some random uses you need to know, definitely for jewelry. A lot of girls, even some guys, have jewelry with diamonds in them. Okay, they are used for glass cutters as discussed before. Okay, they are used for drill bits. I'm just gonna write them all because they're probably gonna come as choose, select all, and apply. Diamond saws. That would be so cool. Imagine a diamond saw, okay? And then rock cutters, or there was another term for it, which is rock borers. I don't know how to, like, it's borers, just like it's the same meaning as cutters. And also abrasive material. So we finished the diamond. We will move on to something else, which is called graphite. Okay, so now we move on to graphite. Now, what is graphite? Graphite is a layered structure of linked hexagons where every carbon atom is bonded to 3 others, leaving 1 free electron that forms a cloud of electrons within layers of graphite. So let me just write. Alright, so this is it. Graphite is a layered structure of linked hexagons where every carbon atom is bonded to 3 others, leaving 1 free electron that forms electron clouds through graphite layers. So now we are going to discuss the properties of graphite. Okay, so we know that graphite is soft and slippery. Okay, why is it soft and slippery? It's due to the weak van der Waals forces between the layers. So remember, we have layers through the electron clouds, and in this layer we have weak van der Waals forces that causes them to be soft and slippery. Another thing is that it conducts electricity. Why does it conduct electricity? Due to the free electrons, electricity, due to the free electrons that are found in the layer or the electron clouds, okay? Another term is free delocalized electrons. Now, graphite is also hard due to the strong forces between the carbon atoms. So look, let's say this is what it looks like. Okay, sorry, I'm not the best artist. And then there's like another layer and whatever here. Here. So in this gap over here, I'm gonna color it in blue. This gap over here, it is what? This is the cloud or the layers in between. So when we're talking about it being hard, we're talking about this actually and not the layers. So this has strong covalent bonds that causes it to be hard. But in the layers, when we're talking about it being soft and slippery, it is here. It has the weak van der Waals forces. Okay? Then it also has a high melting and boiling point. I don't think you can boil it. We're just gonna say a high, what is this? A high melting point. Because I don't think you can boil graphite. That would be really weird. So a high melting point. Why exactly does it have a high melting point? Due to the strong covalent bondings. Now let us discuss some uses. It has fewer uses, to be honest. So we have furnace linings. We also have pencil tips, okay? And aside from that, we have electrodes, okay? Because graphite is inert, yet it conducts electricity. So electrodes and lubricants, because it's soft and slippery. So we finished the graphite. We move on to the last thing, which is silica. Okay, so what is the title of this page? It is actually giant molecular structure. Okay, so this is silica or SiO2, which is also referred to as silicon IV oxide. Silicon IV oxide. It's the same thing as SiO2, okay? So what about the structure of silica? It's the same as a diamond in that it's a tetrahedral structure where every silicon is strongly and covalently bonded to 4 other oxygens. So I'm gonna write it. So that is pretty much the structure of silicon. Now we are gonna be discussing some of the properties. So properties. What about silicon? Silicon, okay, doesn't conduct electricity because it doesn't have any free electrons. So these properties are almost similar to diamond, so it doesn't conduct electricity. Okay. Then another property is that it has a high melting point but lower than diamond. So I'm just gonna write high melting point, but it is way lower than the melting point of diamond. And then it is hard, but it's not harder than diamond because diamond is like probably way harder. And now I'm just gonna write it here so I will not waste my digital storage. Okay, its use is for microchips in computers. Alright, so that's pretty much it for chapter 9. Thank you guys for watching. I hope you enjoyed and have a wonderful day.